We'll continue talking about vectors today. We introduced three-dimensional space and objects like planes and spheres last time. And today what we're going to do is talk about vectors. So we hadn't talked about vectors in three-dimensional space yet. The good news, as we mentioned last time, is that they're very much like the vectors in two-dimensional space with minor differences. Okay, so let's look at the book. We had a definition first, so we want to find out about the magnitude of a vector in three-dimensional space. And as you can see here, so in the picture right there, we have a vector. Let me draw on top of it so that you can appreciate it. And this vector has a tail and a head. And the tail and the head are these points with coordinates x1, y1, c1, and x2, y2, c2. And last time, we already found how to figure out the length of the distance between 2 points, or the length of a segment. And it was exactly this formula that you see right here on top. So that's essentially all we need, right? All we need to do here is to do the difference of the x coordinates, square it, the difference of the y coordinates, square it, the difference of the z coordinates or c component, square it, add those three numbers and take the square root. And that would be the length of the vector, all right? So then you can see, if we scroll further down the page, it's written right here, okay? The magnitude of a vector. Okay, so something else, we also talked yesterday about how in the plane we had two special vectors that were convenient, the I and the J vector, the 1, 0 and the 0, 1 vector. So here we are going to extend this to three-dimensional space. So in R3 we have these three special vectors that are called I, J, and K. And they go again in order, in alphabetical order, I, J, and K. And they correspond to, in the same alphabetical order, X, Y, and Z. So I is where the X is 1, and the other two coordinates are 0. J is where the Y is 1, and X and Z coordinates are 0. And K where Z is 1, the C component is 1, and the other coordinates are 0. Okay? Let's see. Okay. What else? So any vector that you want, you can write as combinations of I, J, and K. You can see them visualized right here in the picture on the left. You see the vector I is the red one. Then in light blue, we have J in the y-axis and K in the y-axis. So there are the three unit vectors that are at each one of the coordinate axes, right? Like X, Y, and Z. You know, like towards you, they will look like this, right? X, Y, and Z, right? These three vectors, okay? And the good thing about it is that then you can write down any other vector as a combination of X, Y, and Z. And this is illustrated on the picture on the right. If you write a vector with components v1, v2, v3, you can write it as v1 times I plus v2 times j plus v3 times k. And we'll do a bit more of this with a specific example shortly. So we want to do now example 6. We'll go to the page now. And example 6 is precisely about that. So we're gonna have 2 points. Let me go back to the page. So example 6, we have the following points. We have the point P, which coordinates 5, 3, 1, and the point Q with coordinates -7, 8, 1. And Part A first asks us to express PQ, the vector PQ, in terms of I, J, and K. Remember that when I write it, I put the arrows because I cannot write bold, right? But in the book, all of these numbers are written in bold, bold font, okay? So here we go. How do we do it? Well, we first calculate PQ, and we've done this before, and in two-dimensional space, and it's no different here in three-dimensional space. So all we need to do is do the head minus the tail, all right? So head minus tail, right? That's what you need to remember. So to get the position vector, it will be -7 minus 5, comma, 8 minus 3, comma, 1 minus 1. Right? So this is a vector -12, 5, 0. And then the point is that we can write this in the following way, right? We can write it as following. It's like we split each one of the components. So it could be like the vector -12, 0, 0, plus the vector 0, 5, 0. And then I don't have z component, but if you want, I can write 0, 0, 0 for the last one, okay? Then we can take the constants out because we know we can take constants out of vectors. So this would be 1, 0, 0. This would be, they take the 5 out, take this 5 out, so it will be 5 times 0, 1, 0. And then here will be like taking the 0 out if you want. Okay, and that's great because these are precisely the I, J, and K vectors. So this is -12 I plus 5J plus no 0K. You don't need to write this part, by the way. The 0K, if you want to just not write it, that's perfectly fine. Because not adding anything or adding 0 is exactly the same. Okay? So notice how you don't need to do this work next time also. I mean, I did it right now to show you how it happens. But in reality, you can go from here to here directly. Not a problem. You can go from here to here directly. You just need to remember that the first one goes with I, the second one goes with J, and the last one goes with K. So the X component with I, J component, Y component with J, Z component with K. All right? Easy peasy. Really, really not that big of a deal here. Okay, part B. Part B now is asking us to find the magnitude of this vector. Okay? And this is, again, what we just learned. The formula is the same. It's very similar to we just use the formula of the distance between 2 points. So since we already did the distance, see, we don't need to, we could have done like, -7 minus 5, 8 minus 3, 1 minus 1, or we could simply use that we already have the components here, right? So either way, I'll write it both ways. So we can write it as follows. So the magnitude of PQ could be, I wanted to see these points here. So it's -7 minus 5. So big square root of -7 minus 5 square plus 8 minus 3 square plus 1 minus 1 square. And that's 12 square, or -12 square, plus 5 square, plus 0 square. And that's the part that I was telling you. Since we had already found the position vector for PQ, -12, 5, 0, you could have gone directly and from here to here, right? And instead of writing this first part, you could have gone from here to here because you already know what is the position vector. So all that is left now is to figure out what this is. This is 144 plus 25. That's 169, and that's actually the square root of that is 13. So the length of this, the magnitude of this vector is 13 units. All right, we're good. Next part, part C. It says now find the position vector of magnitude 10 in the direction of PQ. Okay, and we learned how to do this in 2 dimensions for vectors in the plane. And the procedure here is exactly the same. So what you want to do is first figure out your vector and make it point in the same direction, but of unit length, right? So instead of being a long vector, you know, a long vector like this, you want to make it shorter so that now it's only unit length, but pointing in the same direction. And the way we do that is by multiplying by 1 over its magnitude, right? So that's the first step. So first step, find unit vector pointing in the direction of PQ. And that's easy, right? We just do 1 over its magnitude, PQ. And 1 over its magnitude is 13, 1 over 13. And the vector is negative 12, 5, 0. That's what we learned, right? That's the position vector corresponding to PQ. So now you just multiply the number inside. It will be negative 12 13ths, 5 13ths, 0. Right? So that's my unit vector. And now, okay, so that's not what the question asks. The question asks, what is the position vector of a magnitude 10? So to make it now magnitude 10, or any other number for that matter, the only thing you need to do is to multiply this unit vector by, in this case, 10. But say we wanted it of being 23, then we just multiply by 23. As easy as that, right? So here is the requested. So here is the vector of length 10 in the direction of magnitude, or magnitude and length is the same, it's a synonym, in the direction of PQ. Here it is. We just multiply 10 times this one, the one we found before. So this would be negative 120 13ths, 50 13ths, 0. This vector has length and it points in the direction of PQ. All right? That's how it's done. So as you can tell, it's the same type of work we did before, or with the only difference of having an additional component, an additional coordinate, right? The Z or the J, whichever way you want to call it. Hey, by the way, this is wicked. Let's write it like that. So this is actually negative 120 over 13I plus 50 13ths J. And no K. So that's good. Just to get a little practice into using I, J, and K. Okay, questions? Good. So we'll move on now to the next section. The next section is called dot products, and we're going to spend a couple of days. So today and tomorrow, we'll be talking about this. And so this is going to be a new operation that we're going to define, and I'm gonna go right ahead and define it, and then we're going to discover some properties about it, and we'll talk about why this dot product is actually useful. It's actually very, very useful to figure out how vectors are related amongst themselves. So here is the definition. Let's go right ahead and write the definition. Given two non-zero vectors U and V in 2 or 3 dimensions, doesn't matter, the procedure will be the same. their dot product is defined as, here we go, u dot b, and that's how you use a dot. U dot b is the magnitude of u times the magnitude of b times the cosine of theta. And I need to tell you what this theta is, where theta is the angle between u and v, with measured between 0 and 180 degrees, between 0 and pi. And there's a bit more. If u is 0, if u is the 0 vector, or v is the 0 vector, then u dot v, the dot product of u and v, is 0. And theta is undefined. So there is no angle between those vectors, because there is one of them is just a point, right? Or maybe both of them are just the origin. Okay. All right. So let's digest this definition. Let's try to understand it. And the first very, very important point here to note is that this is an operation that takes two vectors, right? So notice this. So we have u dot v. And this guy is a vector. And that one is a vector 2. So you take two vectors and you operate with them. But what is the answer? But the answer is a scalar, right? This quantity on the right is just a number. See, the magnitude of u is some number. It's how big the vector u is. This is the magnitude of v, is how big the vector v is. And this is a number between 0 and 1, between -1 and 1, right? The cosine. The cosine of an angle between 0 and pi is a number between -1 and 1. So this is a number, right? This is a scalar. You need to understand that this is an operation that goes like that, right? You take two vectors and out comes a number, right? So scalar. Let me put it here, i.e. a number. More importantly, not a vector, right? So it's an operation that takes two vectors and out comes a number, okay? Now, there's some interesting diagrams on some special cases. First, if we have two vectors that are pointing in the same direction, right? So let's try now to make some pictures. So some examples here. I'll show some better pictures in a moment, but if you have two vectors pointing in the same direction, so for example, say this vector u and this vector v, and they point in the same direction, right? So then what happens when you do u times v? Well, it's supposed to be the magnitude of u times the magnitude of v times the cosine of the angle. But what is the angle with two vectors that are one on top of the other? What is the angle between them? Yeah, there is no angle between them, right? There's the angle between them is 0. So here, theta is 0. And what is cosine of 0? Well, that's 1, right? So then this just becomes the magnitude of u times the magnitude of v. So you just multiply how big they are, the two vectors. It's as easy as that. So that's interesting. One that is a bit more interesting, in my opinion, is when two vectors are at 90-degree angles. So imagine now that you have this situation. We have the vector u, and your vector v is perpendicular. So right here, 90-degree angle. Yes? So here, what is the situation? We have u dot v, the same formula, right? Magnitude of u times magnitude of v times cosine of theta. But what is theta here?
Pi over 2.
Yes, 90 degrees, right? Or pi over 2. And more importantly, what is the cosine of pi over 2?
0.
Yes. So that's fantastic, right? Because then this will be 0. Yeah, and that's a very useful thing to remember. And it's the only case in which you get 0, by the way. Because if we look back at the definition right here, see, this is 3 things that are multiplied together. And if u and v are not 0, if you have 2 vectors that are not 0, then their magnitudes are not 0, right? These numbers wouldn't be 0. So the only way that the dot product can be 0 is if the cosine is 0. And the cosine is 0 between 0 and pi only at 90 degrees. So we learn a little bit here, and this is interesting. So we learned that if u and v are non-zero vectors, then u dot v is 0 if and only if the angle between them is 90 degrees. We call these that 2 vectors are perpendicular. All right. So let me show some better pictures from the book, and then we'll keep talking about this dot product. Okay. So like we were saying, so the first case illustrates when u and v point in the same direction. In that case, you just multiply their magnitudes. Now, if the angle between them is acute, so between 0 and 90 degrees, then you're going to multiply by cosine. And cosine is a positive number between 0 and 90 degrees. So the dot product will be positive. Okay, so that also tells you something. So if the dot product is positive, that means the angle between your 2 vectors is acute, right? Then this is the case we just said, that if the angle happens to be 90 degrees, pi over 2, then the dot product is 0. Beautiful. That's also a fantastic way of knowing when 2 vectors are perpendicular. Now, if the angle is obtuse, so if the angle is more than 90 degrees, then the cosine of that will be negative, right? We know that cosine of angles bigger than pi over 2, between pi over 2 and pi, is negative. Therefore, the entire dot product will be negative. So that's another good thing to know. If the dot product is negative, that means the angle is obtuse. Or it could be 180 degrees, right? So if the angle happens to be 180 pi radians, then the cosine of pi is -1, and then what you get is the product of the magnitudes times -1. All right? So this is something nice to remember. We'll do a problem shortly, but before, let's look at an important definition here. This one right here. So when 2 vectors have a dot product of 0, we say that they are orthogonal. That's the new word we're learning. So we're saying 2 vectors are orthogonal if their dot product is 0. Okay, and important to know that this means 2 things. It means that their 2 vectors are perpendicular when they are non-zero, or it means that one of the vectors is 0, right? If one of the vectors is 0, then that 0 vector is orthogonal to everyone else, because when you do the dot product of 0 with anything, it will be 0, according to the definition we learned. Okay, so that's so orthogonal and perpendicular are almost the same word, but not quite, because perpendicular, it only works if you have non-zero vectors, because it means the angle between them is 90 degrees. But if one of them is the 0 vector, there is no angle. But the 0 vector is still orthogonal to all the others. Okay, so that's an important part to note. Okay, so let's do an example. Let's do example 1. It's right here. Let's read it. So we're going to have 2 vectors, part A and part B. So part A is in 3-dimensional space. We have the vector 2i minus 6j and the vector 12k. And we want to compute the dot product. And then we're going to do it for these other 2 vectors in the plane. All right? So let's check it out. All right, so what is the definition? Let's write it here. U dot V is the magnitude of U times the magnitude of V times the cosine of theta, right? Now, so this is the recipe, and we see the ingredients right here. We need the magnitude of U, we need the magnitude of V, we need cosine of theta. Now, from here, we already know how to get magnitudes, so that let's bypass that for a moment. Let's just not concern ourselves with that just yet. So let's start with a new thing, the thing we haven't figured out how to get yet, which is the angle, right? How do we get the angle between 2 vectors? That can be complicated. In fact, that would make this dot product really hard to calculate if you think about it, right? So you have your vectors and you need to figure out the angle. We haven't learned how to do that. How do you get the angle between 2 vectors? So stay with me, because we're gonna find out later on today a more succinct or quicker way to get the dot product in a way that maybe you don't need to figure out the angle, right? In fact, the way we're gonna figure out will help us get the angle, right? It will be, going around in an indirect way, so to speak. But before we do that, let's try to do this problem. So let's plot these vectors. Let's see where they are. So let's try to do a picture here. So here are our axes, 3-dimensional axes. So remember, this is X, this is Y, and this is Z. And we're gonna plot these points. So the U vector is, we go 2 units in the I means the X direction. So 1, 2 units. And then we go -6 units on the Y, -6. So let me continue the axis on the other side. So that would be 1, 2, 3, 4, 5, 6. And then you see where they intersect, and that is going to be my vector. So this is going to be the vector U. All right, so that's U, -2, -6, and no height, nothing on the Z. Now let's check the vector V. The vector V is 12 units on Z. So my scale is gonna have to be different, because otherwise it won't fit in my picture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is my vector V, right? And now, what is the angle between those 2, right? That's what we want to find out. What is this angle from here to here? Right? And it shouldn't be too hard to answer that question, because the V vector, imagine that this is this plane that you see right here is the XY plane. Then that the U vector lives in there, let's say is this green pen, right? That's my U vector. And the Z vector is perpendicular. It's like this one here, right? So what is this angle over here?
80 degrees.
Yeah, 90 degrees, right? So we were really, really lucky. Yes, that's the only way we could have done this problem, as a matter of fact. So we were extremely lucky. This angle equals 90 degrees. So pi/2 radians. So that means the dot product, so that's it. What is the dot product then?
0.
Yes. Yeah. So that's what we learned, that every time the angle is 90 degrees, beautiful, we're done. The dot product is here. So this was extremely easy because, well, they gave us some easy ones, right? I mean, you move this V a little bit, you change it, maybe you put 12K plus I, and then something entirely different happens. And then maybe we don't know how to do it just yet. All right, so that was part A. Let's take a look at part B. So for part B, now we have the vector u. Now it's in the plane, is square root of 3 comma 1, and the vector v is 0, 1. And the plane is easy because now we can create more accurate pictures, and everything is considerably easy, right? So root 3. So root 3 is like 1.7 and comma 1. So right here is root 3. So this is u. And v is 0, comma 1. Right, that's my picture. So what is my angle there? This is the angle between them. And I need it, right? I need it to calculate u dot b. I need the magnitude of u, I need the magnitude of v, and I need cosine of the angle, right? And the good thing here is that this triangle is a right angle, right? So we have a little right triangle here. So that makes it easy for me to know the cosine, right? How do we get the cosine of this angle? The cosine is adjacent divided by hypotenuse, right? So the adjacent is v. The magnitude of v, which is 1, divided by the magnitude of u. And what is the magnitude of u? We should calculate them. So we're going to need them anyways, right? So let's do it here. So the magnitude of u, that's easy. That's root 3 squared plus 1 squared. That's square root of 4. So that's 2. Magnitude of v is 0 squared plus 1 squared. So that's 1. So they have magnitudes 2 and 1. So this cosine is 1/2. So this angle is actually 60 degrees, right? Pi over 3, or 60 degrees. Okay, and that's fantastic. We have all the ingredients. See, we have this guy over here, u that goes here. We have 1 that goes here, and we have cosine that goes here, right? So let's put it all together. What is the dot product? It will be 2 times 1 times 1/2. The answer is 1. All right? Is that clear? Good. So from these two examples, you should be getting the idea that this is going to be hard, right? How do you even get that angle in the first place? Okay, so we're gonna do a little bit of deducing how we could go around figuring out the angle. Okay, so that's what we're gonna be doing now. So how can we? So here's what we want to do. We want to calculate the dot product in an easier way. Without knowing theta. That's really the issue, right? So how are we gonna do it? So I'm gonna actually this time around I'm gonna tell you precisely how we're gonna do it. So we're gonna do a little bit of more work. So we're gonna learn a little bit of geometry. Okay, and the first part from geometry that we need is the law of cosines. So I'll tell you what the law of cosines is. If you have a triangle, and these sides have lengths A, B, and C, and this angle over here is theta, right? And this works with any triangle. So for any triangle with side lengths A, B, and C, okay, and angle theta opposite to the side of length C. So just like my picture it shows, this happens. C squared is equal to A squared plus B squared minus 2AB times the cosine of theta. That's the law of cosines. All right? That is the law of cosines. And it's kind of like the Pythagorean theorem, if you didn't know this, right? In fact, if theta is pi over 2, if the angle is pi over 2, we know cosine of pi over 2 is 0. So if this had been a right triangle, if theta is pi over 2, then this is 0. And look, what is that? That's the Pythagorean theorem, right? So you can think of the law of cosines as a generalization of the Pythagorean theorem. Now, I'm not going to just tell you this is the law of cosines, and now we're going to use it. No, I'm going to show you why this is true. That's so we're going to go really, today we're actually explaining everything. We're not going to leave you hanging there. I'm going to tell you precisely why this is true. Okay, so here we go. I'm going to prove to you the law of cosines. And it's easy, actually. It's not that hard of a proof. I'm going to recreate that drawing from before. And the only thing I'm going to do is draw this height, right? The height over there. And this is theta. Okay, and then that divides this into two pieces, right? This piece and this piece. So I'm going to call this A1 and this A2. And you just need to remember that A1 plus A2 is actually A, right? It's this entire length. Okay? All right. Now, I'm going to deduce to you why this law of cosines is true. And here's how I'm going to do it. I'm going to apply the Pythagorean theorem to those two little right triangles you see here. See, there's this little triangle and this other triangle, right? So let's use the Pythagorean theorem. What do we have by the Pythagorean theorem? We have that b squared is h squared plus a2 squared, right? That's on the little one. And on the bigger one, we have c squared is h squared plus a1 squared, correct? Okay, so now what I'm going to do is I'm going to solve for h squared here. And that would be b squared minus a2 squared. And then we're going to plug that in here. And what do we get? We get c squared equals b squared plus a1 squared minus a2 squared. Right? Okay. And why is this helpful? Well, you see in a moment. So the way this is going to be helpful is in the following way, right? So now solve for a1 here, because I want to involve a. See, look at the formula we want. We're getting there, right? We have c squared, we have b squared, and then I have this, but I don't want this. I want a squared and I want that. So I'm gonna try to get rid of a1. How am I gonna get rid of a1? I'm gonna solve for here. So here, a1 is a minus a2. So we're gonna plug that in here. Okay, let's see what we get. We get c squared equals b squared plus a minus a2 squared minus a2 squared. Now I'm going to expand that square. That's going to be a squared minus 2a a2 plus a2 squared minus a2 squared. And that's actually nice because these two cancel, right? So this is our situation so far. I have b squared, a squared, and minus 2a, a2. And I'm going to show you what we wanted. We wanted this. We're almost there, right? We have the a squared, the b squared, and we only have these are almost the same. And we're almost done. There's only one step missing, which is to get rid of the cosine. And that's easy if you look at this triangle here. See, on this right triangle, what is the cosine of theta? Well, cosine of theta is supposed to be the adjacent divided by the hypotenuse. So that's a2 over b, right? And better yet, I can solve for a2. So a2 is b cosine theta. And this is the last step of the puzzle. I just gotta put that in here now. And when I do, what do I get? I get a squared plus b squared. I just switch the order of these two. Minus 2a b cosine theta. Voila. There you have it. The law of cosines. I just proved to you. All right? You with me? Okay. So we're going to need that. Let me put it back here. The law of cosines. And now we're going to use it to calculate the dot product, right? That's what we wanted in the first place. We wanted to know the dot product. And to do that, I need to come up with another picture. So I need to show you now how the picture of U and V looks like. So here's a generic U. Imagine that we are in 3 space. So there's the vector U. And here's the vector V. Okay. And it has an angle between them, an angle theta. All right. Now I need to have a triangle to apply the law of cosine. So I have to complete this one over here, right? So what is this vector over here? This green vector. What is it? And we did this yesterday or the day before, maybe. See, if I add V and the green vector, so if I go orange and then green, I end up the same as U. So that tells you that the green vector is actually V minus U, right? We talked about how to do the difference. So this is V minus U, right? Okay, so now let's apply the law of cosines to this triangle over here. So by the law of cosines, so for that, this is going to have to be A, this is going to have to be B, and the length of this is going to have to be C. I mean the lengths, right? The magnitudes. So what I mean to say here is that magnitude of C is actually, write it the other way around. So C will be the magnitude of V minus U. V will be the magnitude of V, and A will be the magnitude of U. All right? So let's now use the law of cosines. Is going to be the magnitude of U squared plus the magnitude of V squared minus 2 times the magnitude of U times the magnitude of V times cosine of theta, right? That's what the
Professor,
is.
I just have a question. How come it's not U minus V?
Should be U minus V, yes. You are right. It's not going to matter because I want the magnitude, right? So or what I was doing is not, it doesn't matter if I use this one or the one pointing in the opposite direction, but you are right. According to my picture, it should be u minus v.
Oh, okay. Thank you.
Okay, and so that's, we don't need the law of cosines anymore. We used it here. So I'm just gonna remove this from the top, and so we have more space. And, but the important thing to note here is that, note, this is precisely u dot v, right? That's without the 2. This part is u dot v. So this is already telling me that maybe there's a better way here to get the dot product. So now we only need to do a little bit of work here to figure out these magnitudes. So imagine for a moment that u is the vector u1, u2, u3, and v is the vector v1, v2, v3. So then what is the magnitude of u, the magnitude of v, and the magnitude of u minus v? That's we need, right? So let's start with the magnitude of u. The magnitude of u is u1 squared plus u2 squared plus u3 squared, square root of that. The magnitude of v is the same but with these, and the magnitude of u minus v is the same, but first you subtract u1 and v1, then u2 and v2, and last u3 and v3. Okay, and something else that I like about this a lot is that everything is squared. So when I square these, I'm gonna kill the square roots, right? So let's put now everything back into our expression over here. So this is going to be u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared equals. So this one is u minus v quantity squared. Magnitude of u squared, that's u1 squared plus u2 squared plus u3 squared. Magnitude of v squared, that's v1 squared plus v2 squared plus v3 squared, and minus 2 times u dot v. Right? Now, there's not, sadly, there's no shortcut here. We have to expand these, but good things will happen. So when I expand these, this is u1 squared minus 2 u1 v1 plus v1 squared plus u2 squared minus 2 u2 v2 plus v2 squared plus u3 squared minus 2 u3 v3 plus v3 squared, and that should be equal to u1 squared plus u2 squared plus u3 squared plus v1 squared plus v2 squared plus v3 squared minus 2 times u dot v. Right? Now, almost done. Notice how this u1 squared cancels with this u1 squared, this u2 squared with this u2 squared, this u3 squared with this u3 squared. Then the v1 squared, the v1 squared, v2 squared with v2 squared, and v3 squared with v3 squared. So what is it that remains? Let's figure it out. Here's what remains. We have negative 2 u1 v1 negative 2 u2 v2 minus 2 u3 v3 equals negative 2 u dot v. And last step, divide everything by negative 2. And what are we going to get? u1 v1 plus u2 v2 plus u3 v3 equals u dot v. Wow. So simple now, right? Look at this, how easy it is now to figure out the dot product. See, we don't need to get the angle. All we need to know are the components. We need to know what is the x component, the y component, and the c component, right? U1, U2, U3, V1, V2, V3. And then all we need to do is multiply the x components. Bam, add, multiply the y components right here. And last, multiply the z components. That's it. That's it. That's the dot product, right? We didn't need to get the angle anymore. Yes? So now this gives you a brand new way of figuring out the dot product, and one that does not depend on the cosine of the angle, right? In fact, we could use this to get now the cosine of the angle, right? Because what is it that we have now? Let's put it over here. So we have the old way of getting the dot product, which is magnitude of u times magnitude of v times cosine of theta. That was the definition. And now our new way is just do u1 v1 plus u2 v2 plus u3 v3. Right? So think about it. Now you can use this to get the cosine. How can you can simply solve for the cosine. So you can solve for cosine theta. And cosine theta will be u dot v divided by the magnitude of u times the magnitude of v. And you can do this easily. It's just u1 v1 plus u2 v2 plus u3 v3. And the magnitudes are easy to do as well. It's u1 square, u2 square, u3 square, square root of that, v1 square, v2 square, v3 square, square root of that, right? So this is now a quick way to figure out the angle, right? We can now get the cosine of the angle of two vectors, and if you know the cosine, then you know the angle, right? Okay. Okay. So now, if this seemed a little bit over the top for you, don't worry about it. See, we only need to do this once, right? Because now we know the formula. Now we could use this knowledge to figure out specific problems. So that's what we're going to be doing now. Let's check example 2. All right, this is what we have. It says let vector u is root 3, 1, and 0. Vector v is 1, root 3, 0. And vector w is 1, root 3, 2 times root 3. Here is a question. Part A, compute u dot v. Part B, find the angle between u and v. And part C, find the angle between u and w. All right, let's do it. First part. See, now we're gonna do the easy way, of course, right? So how do we do u dot v? Well, we're gonna do the new way we discovered. So it will be u1 v1 plus u2 v2 plus u3 v3. And that's easy, right? Because we have the components right here. This is u1, root 3, and this is v1, 1. So it's root 3 times 1 plus u2 times v2 plus 0 times 0. What is this? 2 root 3. That's it. We're done, right? That was painless. No problem. Now, let's calculate the angle. How can we get the angle? Well, to get the angle, we remember this, that the cosine is the dot product divided by the product of the magnitudes. So, this is part A. For part B, we remember that the cosine is the dot product divided by the product of the magnitudes. We already calculated this, and we just need to now calculate the magnitudes. The magnitude of u is √3 squared plus 1 squared plus 0 squared, and the magnitude of v is 1 squared plus √3 squared plus 0 squared. So this is 4, square root of 4 is 2, and this is also 4. So square root of 4 and a square root of 4. So one of these two cancels, so we get square root of 3 over 2. Yes? And then if the cosine is square root of 3 over 2, what is the angle?
Is it pi over 6?
Yes, 30 degrees, right? So it's like this one over here, half an equilateral triangle, where this is 1, this is 1/2, and this is square root of 3 over 2. Very good. So that was easy peasy, right? So it's a fantastic tool. The dot product is a great tool to figure out the angle between vectors. Okay, and one last, let's see now the angle between u and w. So it's similar, right? So we only need to do now u dot w divided by magnitude of u times magnitude of w. Now, what is u dot w? Let's go back. U and w are right here. So now, you don't see it right now, but I'm going to write it. So it's square root of 3 times 1 plus 1 times square root of 3 plus 0 times 2 times square root of 3. And then the magnitude of u is, we did that one before, it's right here, is √3 squared plus 1 squared plus 0 squared. And then the magnitude of w is going to be, is these numbers right here. So it's 1 squared plus √3 squared plus 2 √3 squared. Okay, so let's see, this is √3 and √3. This one we knew is 4, so that's square root of 4, so that's 2. And this one will be 1 plus 3 plus, what is this one? 4 times 3, 12, plus 12. So this is 16. We have 2 square root of 3 divided by 2 times, this is 15, 16, square root of 16 is 4. This is square root of 3 over 4, right? Okay, so that's the cosine. The cosine is square root of 3 over 4. Now, what is the angle? Well, it's not one that we know, right? So you can write it as this. You can use the arc cosine function. So it's arc cosine of square root of 3 over 4. The book says that it's about 64.3 degrees, right? In case you were wondering, but that's good. You can just leave it like this as the arc cosine of the square root of 3 over 4. Okay. Questions? So there's one additional thing that I want to see in the last couple of minutes. It's a quick one. So let's go to the page in the book 830. These are some properties of the dot product, right? And some of these are kind of very easy to know. Others you would need to prove, but with this new way of figuring out the dot product, they're actually extremely easy to check. So the first one, it says that the dot product is commutative, meaning order is not important. And we kind of know that because what is the definition? The definition is the product of their magnitudes times the cosine of the angle in between them. So there is no reference there of which one is first, which one is second. It doesn't matter, right? The second property is the associative property when you multiply by a constant. So if you multiply by a constant, you can multiply the constant on the first, or you can multiply the constant on the second as a scalar multiplication. And in either way, you get the same answer. And the last one is the distributive property. If you do the dot product of u times v plus w, you can do first u dot v and then u dot w and then add these two numbers, right? Now there's this distinction, important distinction to make here in this little equation. This plus over here that I just circled, that's addition of vectors. That's when you add up two vectors together. Whereas this plus over here, the red one, that's just adding numbers. It's just adding one number and another number. So even though you see plus here and plus here, they're different operations, right? This is addition of vectors, the blue one, and this is addition of numbers, the red one, addition of scalars. And yet it works out, right? An easy way to check this property number 3 is to use the definition of dot product as uv1 plus uv2 plus u3v3. Okay, and one last thing is that even though we did this formula, this new formula right here at the top, this formula, we did it in 3 dimensions. If you want to do it in 2 dimensions, it works the same way. The difference is there's only going to be 2 of these, right? So the dot product you can also do in 2-dimensional space by just using u1 and u2 and v1 and v2. It's even easier, all right? I just wanted to let you know that. The proof will work the same way. In fact, the proof works the same way if you think that u3 and v3 are both 0. If these two are 0, then there's nothing here, right? And then it works exactly like we wanted it for the 2-dimensional space. Okay? All right, so this is going to be it for today. Tomorrow we'll continue this section. What we're gonna be talking about is what happens when you take one vector and you project into another one, right? How can you calculate the projection of one vector onto another? And the dot product will be especially useful for that. Okay, so are there any questions before we stop today's session? I, by the way, posted already solutions to, I mean, not solutions, your scores for exam number 2. I finally finished grading exam number 2, and it's right there. Some people have asked me if I'm gonna upload your actual exams, and I don't have the bandwidth to do that. I wish I could, but it would take me a long time to scan all your tests and then upload them. But if you want, you can always come to office hours, and then I can show you your exam. I mean, put it on the screen, and then we can check it. You can check page by page. All right. All right. Okay. See you guys tomorrow. Same time. Stay safe.